Welcome back. In this video, we're going to do another example with limiting reactants, and I'm going to show you a different method that you can use to predict the limiting reactant. All right, now the questions in this write-up are a little bit different. They're actually asking us which reactant is in excess. And there's no direct way that you can figure out the reactant in excess. You're kind of finding the limiting reactant, and the excess reactant is whatever is not the limiting reactant. In the follow-up questions, we're going to be figuring out how much of the excess reactant remains after the reaction is complete. And we're going to be predicting theoretically what the mass of the precipitate will be once the reaction is complete. So we have a solution of barium chloride and a solution of sodium sulfate. I've gone ahead and written down the masses of each and the molar masses of each. And what we're going to be doing here is figuring out the moles of barium chloride and sodium sulfate. So maybe pause the video and calculate that on your own at this point. All right, so if we were to go ahead and find the moles of each, you should be well versed in how to do this. We take our mass and we divide it by the molar mass to figure out our moles. So we get, for barium chloride, we do 9.8 divided by 208.23. And we get a number of moles of 0.047. I'm just going to round it for now. All right, let's do the same for sodium sulfate. 5.1 divided by 142.05. And we get 0.036. All right, so what is the limiting reactant in this case? Well, to determine the limiting reactant, you need to be able to look at the mole ratio and figure out if the calculated moles that you have of each fit, or how they fit that mole ratio. And this example is actually kind of straightforward because it's a 1-to-1 ratio between these two reactants. It's a 1-to-1 ratio. So just by looking at these numbers, which of them do you think is going to be consumed first? Well, it's going to be the one that is stoichiometrically lower. It's the one that, if this is a 1-to-1 ratio, I can just look at these numbers and tell that, well, I've got more barium chloride than sodium sulfate. And if it's 1-to-1, that means to be consumed completely, you would need to have at least 0.036 moles of barium chloride. And I've got actually more of that. I've got 0.047 moles of barium chloride. So with these numbers, you can actually, and with this mole ratio, you can actually just look at this and say, this is lower. I don't have enough of this to react with all of the barium chloride. That means sodium sulfate will be the limiting reactant and barium chloride will be the excess reactant. So I can tell already that it's going to be barium chloride. But there is another way. This method of just looking at them and seeing how they fit the mole ratio is similar to what we saw in a previous video. I did say that we're going to look at another method, and this one I like this method because you can actually answer question C at the same time they figure out what the limiting reactant is. You can actually use this method to predict your theoretical yield of product at the same time that you determine the limiting reactant. All right, so what is this other method? So what we can do is we assume that each reactant is the limiting reactant. So I assume sodium sulfate is the limiting reactant, and I'm also as a second option, I'm going to assume barium chloride is the limiting reactant. Now, just bear with me. We already know that barium chloride is not the limiting reactant, but I'm just going to show this method to show you why it works too. So if we assume sodium sulfate is the limiting reactant, what we're going to do is then figure out, okay, how much of the precipitate, barium sulfate, we would make given that this is the limiting reactant. So number of moles of barium sulfate that we would make is going to be equal to the number of moles of sodium sulfate, because we're assuming it's the limiting reactant, times the mole ratio. So it's a 1-to-1 ratio, and the number of moles of barium sulfate that I would make, in effect, is actually just the number of moles of sodium sulfate I start with, because it's a 1-to-1 ratio. So in this case, I would make 0.036 moles of barium sulfate if sodium sulfate was the limiting reactant. Now, if I assume that barium chloride is the limiting reactant, that should be sulfate. If barium chloride is the limiting reactant, I'd go through the same operation. And I'd find that I'd make 0.047 moles of barium sulfate. And you can actually use this method to determine the limiting reactant in every problem. The limiting reactant is actually the reactant that produces the least amount of product. And the reactant that produces the least amount of product is sodium sulfate. So when I make my assumptions about each reactant being the limiting reactant, the reactant that produces the least amount of product is going to be the limiting reactant. And in this case, this is just to show you that yes, this method works because we did predict accurately that this was going to be the limiting reactant, sodium sulfate. And even in other reactions where the mole ratio is different, let's say it's like 2-to-1 or 3-to-2 or 2-to-3, some weird numbers like that, you can still use this method. The limiting reactant will be that reactant which produces the least amount of product. So in this case, once again, it is sodium sulfate. So we know then that barium chloride is in excess. So we know that this one works, that one doesn't. Okay, so barium chloride is the excess reagent. Now the follow-up question, how much of the excess reactant remains after the reaction completes? So we know that it's a 1-to-1 ratio between barium chloride and sodium sulfate, and the number of moles of barium chloride required to react with sodium sulfate, in this case it's a 1-to-1 ratio, so it's actually going to be 0.036 moles. So once all that sodium sulfate is consumed, you would also have consumed 0.036 moles of barium chloride. Now, how much remains? The number of moles of barium chloride remaining equals 0.047 moles minus 0.036 moles. And I think that works out to roughly 0.011 moles. So I'd have a little bit left over. I'd have 0.011 moles of barium chloride left over after the reaction is done. Okay, last question. What is the mass of the precipitate? Whenever we're trying to predict the mass of a product, we need to use the moles from the limiting reactant to predict how much product I'm going to make. And we've actually already done that. The number of moles of barium sulfate that we would make if sodium sulfate is the limiting reactant, and we know it is, is 0.036 moles. Okay, so that's why I like this method, because you can actually predict in moles how much product you'd make and determine the limiting reactant in the same operation. So we know that we'd only make 0.036 moles of barium sulfate. To figure out its mass, I need to multiply by its molar mass, and the molar mass of barium sulfate, let's see, I've got 1 barium, so 137.33, plus sulfur is 32.07, plus 4 oxygens, that's 4 times 16, is 233.4 grams per mole. 233.4 grams per mole, and I multiply that by 0.036. And it looks like I would make, let's say 8.4 grams of barium sulfate. And there you go. So this problem was actually pretty straightforward because the ratio is really nice to work with. 1 to 1, there's a 1 to 2 ratio, but we didn't really use the 2 here. So it was, in effect, we're just using 1 to 1 ratios throughout the whole problem. This is not always going to be the case. So the way that would show up, once the ratios are different, they'll show up in these conversion factors. So these ratios might be 1 to 2 or 2 to 1. They're going to be different from 1 to 1, but you're still going to set it up the same way. All right. Now, it also might affect this calculation, like your work for questions like B. When you're trying to figure out how much of the excess reactant is remaining, you also need to apply a mole ratio there to figure out how much of the excess reactant was required. All right, so pay attention to your mole ratios. They're not always going to be 1 to 1 like they are in this problem. And that's why we spent, a fair bit of time just going over mole ratios and understanding what they mean. All right, so hopefully you it made a little bit more sense what we're doing in this video. We did use a different method for determining the limiting reactant. What you do is you assume each reactant is the limiting reactant, and you calculate how much product you would make under each assumption. And the reactant that yields the lowest amount of product is the limiting reactant. The nice thing about this method is that you can determine the limiting reactant, and you can also predict the amount of product, which we call the yield, that we would get out of the reaction. All right, that's it for this video. I'll see you in the next one. In the next few videos, we're gonna talk about yield, theoretical yield and percent yield, and all that stuff. All right, if you found this kind of confusing, or if you'd like to see another example where the mole ratio is different, just leave a comment or send me an email, and I'd be happy to do that. All right, bye.